For homework 3, part C, we're going to take our initial steady state conditions, which we have reached, and then from there simulate what would happen if we were to change the reflux ratio. So one thing we need to do is change our function in order to take the reflux ratio as an argument. And then one thing that was corrected, I noticed that our reboiler and condenser were just staying completely constant and not changing, and that was because I had M0 instead of MT and MB here. So that was fixed, and now, as you can see, our condenser has a little bit more than our M0, and then our reboiler uses the controller in order to get down to 12. So what we need to do now is we'll take this, and we will copy it here. Our new T end is only going to be 25 seconds, and we need to use a lambda function in order to change our R without needing an initial value. So T vec of our right hand side, which we will have our T vector and our R value, which will be 1. And then for this, we have our res1, so our first result of our t-plot up here, so our steady state final values, so those will be our new initial conditions, so our res1s, and we want all of the values, so all of them, and then we want the very last value, and then red u dense output still equal to true. Our t-plot is going to be the same, in which 0 t end we want 50 points, but it's 25 seconds this time. And then we'll call this our res2, which is going to be our res t-plot as well. And then we need to just change this to our res2. And then we want fig2, fig2, and fig2. And we can see if this works. Takes 2 arguments, but 3 were given. Oh, we changed this R, but we didn't run it. So now this one no longer works, but this one should. Which one? No attribute SOL. Res2. Oh, so we just want res here still, not res2. And then we'll show our figure, and it should be fig2. So this is with what we calculated to be our steady state. So if we keep our R value the same, we should expect it to be the same as well. So now, if we were to increase our R value to 2, take a look here. You can see it fluctuates in our mass accumulation a little bit, but you can see our separation begins to get a little better with a higher concentration of our tops and a lower concentration in our bottoms. And as we continue to increase our R value, we can see that this value of 0.76 and our bottom of 0.11 will continue to increase in the top and decrease in the bottom. So now we're all the way up to 0.77, and then finally, if we get to our final step of 5, you can see 0.78 nearly, and our bottoms are down below 0.1. So increasing our R value is improving our separation in our system, and that's how we would simulate that. For the last part of homework 3, we're going to make some McCabe field diagrams. So we'll create a new figure, call this figure 3, make subplots. We want 1 row, rows equal 1. And our columns, we will have 4 for each time step. So what we need to do now is that for I, it will be the same as this up here. But we're going to want to transpose each of these in order to rearrange the way that they're they're ordered as an array, so we can take different values. So now we know in here our y's are going to be equal to our x's, but which will be on our xy concentration diagram or equilibrium curve, and we will calculate that using this equation. So that will take for each x in our series here, and then calculate a y. So to make that curve, we will have our YMCs is going to be equal to our np.pete. We're going to want our y's, and then because we'll have one for each x, we'll take our second one all the way up into the last, and then we will repeat that twice. Expected. And then our XMCs are going to be equal to array. So np.r. We want our first x, so x0. Then we will want to repeat our 1 through our second last, repeat, and then we will be repeating our x values from our second to our second last, and we will be repeating them twice. And then lastly, we will add on our x value of our very last one. Okay. We quickly need to add our equilibrium curve, which is in this case just determined by our value of alpha. So our x plot for this is going to be just linearly spaced points, so np lin space from 0 to 1, which will be our x concentration, and we'll have 100 points. And then we need our y plot for our curve to be equal to, it will be the same equation we use to determine our y's, but for each spot with an x, we will replace that with our x plot. So this will just make an equilibrium curve, which we can use for our plotting purposes. Get rid of plus x plot. So we got those two, and then we will add that to the graph. So fig3 dot add scatter. We want our x's to be our x plot. We want our y to be our y plot. We're going to name it. Name is going to be an f string, so we'll just call it whatever I we're on for now, and then this is in row is equal to 1, and then our column will be equal to I. We now need to add our y equals x line for each figure, so our figure 3 dot add scatter is going to be equal to our x. It's just going to be equal to a point. Our y will also be equal to a point. And using this point, 2 points make a line. So we move on. Mode is equal to lines. This doesn't need this doesn't need a name either. We'll make sure it's a line. And then because our I starts at 0, this will be I plus 1. And then we'll need the same thing for this, adding x equals y line to each of our things. And then lastly, we just need to add our actual values. So fig3 dot add scatter, and then now our x's will be equal to xmc. Our y's will be equal to ymc. Our mode will be, again, lines. And our rows and columns will be the same. So hopefully this works. No. Figure has no attribute. Spelled scatter wrong. Not ideal. What do you mean? Pair is out of range. What? I see. So our I value is becoming too large, meaning we're out of range of our 4. So what we need to do is we only want 4 graphs. So our m's and our x's is going to be np.split. We want our res2 here. So we have our res2. And we only want, we need all of the values, but we only want one every 16. And then we'll split it into 2 different parts on the first axis. Maybe that's syntax. What do you mean? You can, oh, this needs to be brackets. Brackets. And bracket. So, now we hope. Big 3. There we go. What you can see from these is as our time goes on, so what this is doing is it is getting our values for a time step every 16 of our steps. So this will be our initial time, 16, 32, 48. I didn't title the graphs in this situation, but as you can see, this McCabe deal on the left here corresponds to our values here. So you can see our separation is not as good as it is at the end, which can be easily seen here as it's only down to here and then only up to 0.71, and then as our time goes on you can see it's increasing like our separation is here, and as we reach the very end our separation reaches its highest point and then its furthest down point over here, which is what we would expect as our time goes on after we've increased our reflex ratio. Okay.